Good afternoon, everyone. I'm Howard Lerner. I'm the Executive Director of the Environmental Law and Policy Center. Welcome to ELPC Thinks, which we're going to be streaming on Facebook and recording so that others can hear it if they weren't able to join a couple hundred people today. With me is Drew Gronewold. Drew is at the University of Michigan. He's an associate professor of the School of Environmental and of the Environment and Sustainability, the SEAS school. And Drew is going to do his annual update on the state of Great Lakes water levels, what that means for the futures of the Great Lakes. And we'll have an interesting conversation both with Drew and try to create an opportunity for some of the questions that a number of you I know will have. All right. Drew is an expert in hydrological modeling. He's worked with the Army Corps of Engineers and NOAA on Great Lakes modeling and forecasting for a number of years. So you're going to get the current, the latest, the greatest, the update on water levels. And then let's have a conversation. Professor Drew Gronewold. Drew, good to see you again this year. What's in store with the Great Lakes as we go into the summer?
Thanks, Howard. Thanks for the introduction. It's great to be here. I'm assuming now's the time for me to share these slides. Can you quick check? Can you see the slides okay, Howard, and hear me okay?
Everything's fine, Drew. It's come along. It's great.
Great. So yeah, my intent today is give a pretty brief update on the status of Great Lakes water levels, and then, as Howard mentioned, take some time to discuss and answer questions. But I'd be remiss if I didn't start out by first thanking the Environmental Law and Policy Center for the opportunity to speak. And I always need to thank our great team of students and postdoctorate fellows. This is an updated slide of several members of our current team on the top row: postdoctorate fellows and PhD students, master's students, and even a great cohort of undergraduate students at the University of Michigan, without whom this work would not be possible. Several years ago, when a lot of this work was initiated, we had a slightly different team, and I need to acknowledge them as well. And I also want to thank my colleagues who I used to work with at NOAA, at the National Oceanic and Atmospheric Administration. Again, without their collaboration and continued support, none of this work on Great Lakes water levels would be possible. And finally, several of our sponsors who support this work, including the Army Corps, the United States Geological Survey, NOAA, the Great Lakes Protection Fund, the Michigan Department of Transportation, and the Council of Great Lakes and St. Lawrence Governors and Premiers. Finally, I'll mention the bottom right-hand corner. A lot of this work is administered through the Cooperative Institute for Great Lakes Research, a partnership between the University of Michigan and NOAA. So in the next few minutes, what I want to do is first just give a brief introduction and provide some new context for some of this work. And then we'll take a look back at where we were a year ago in May 2022. And then we'll shift to June 2023 present to talk about where we are with water levels. And I'll finish off by talking about future water levels from two perspectives. One, from a seasonal or monthly perspective. Many of you might have questions about what water levels are going to do over the next 6 months to a year. And I'll also talk about water levels at multi-decadal scales. And of course, this is another question people have, particularly from long-term infrastructure planning. So to begin, for this year's update, I wanted to take a moment to provide what is increasingly becoming important, to take a sort of a continental perspective on water when we talk about water levels in the Great Lakes. And what I'm showing here is a map of the major river basins and watersheds across much of North America. Now, the work we're going to be talking about today focuses on the highlighted area you see here, which is the Great Lawrence and St. Lawrence River Basin. But there are other areas where we're doing a lot of work, including the Great Basin in the arid West. There are several lakes there, including Great Salt Lake, Pyramid Lake, and especially Mono Lake, a lake we're doing a lot of work on, as well as Owens Lake, which many of you know is basically gone at this point due to mismanagement, diversions, and an inability to forecast long-term impacts of climate change. So what I want to do is continue to provide sort of a continental perspective on water scarcity and abundance. And finally, I want to mention that one of our PhD students, Viviane Rueda, is doing very exciting work on understanding the U.S.-Mexico Treaty of 1944 and how that's being used to manage waters of the Rio Grande. So again, the take-home message here for this group is, as we continue to talk about the Great Lakes, I think it's going to be increasingly important over the next years and decades to maintain a healthy perspective on water use and agreements all around the country, if not the world. Finally, I'll bring it back to the Great Lakes This is an image I've shown before, which was on the cover of the Chicago Tribune in February of 2021, indicating that the city of Joliet had essentially run out of water. Joliet drew its groundwater at that time from the Cambrian Ordovician aquifer. And as many of you in Chicago know, that groundwater has been drawn down so much that Joliet now has to rely on diverted water through the city of Chicago. This reached a major agreement just a couple of months ago, but I think it's an important point, an important contextual point, that while we often think of the Great Lakes as being an area of water abundance, there are communities, particularly those along the perimeter of the Great Lakes, that either have poor water quality or poor access to groundwater resources. So with that context, let's take a look back at where we were in May of 2022. This image I'm showing here is a snapshot from a tool that NOAA's Great Lakes Environmental Research Laboratory maintains. It's called the Great Lakes Dashboard. And what we're showing here are just a brief period of history of water levels in the top panel from Lake Superior, and in the bottom panel on Lake Michigan and Lake Huron, which we often combine at this scale for one large lake. We have water level records going all the way back to the mid-1800s, but this image is just showing water levels from the mid to late 1990s up until where we were last year in the spring of 2022. The blue dots represent monthly average water levels, and the red line represents the long-term historical average. So in this tool, in this Great Lakes dashboard, and if you're interested in reading more about it, there's a paper we wrote at this point almost a decade ago describing the tool and its origins. Now, with this tool, with a mouse click, you can add certain features like the record high water levels. Now, one of the important features with this record high water level that you'll see is not only the sudden rise in water levels that we were dealing with not long ago, but the fact that many of the monthly record high water levels were set during this 2019 and 2020 period. So last time we met, there was a big question about whether the decline in water levels that you see here following that peak was going to mirror or mimic declines that we had seen in the past. So what now I'm showing on this slide, again, is Lake Superior water levels on the top, Michigan Huron on the bottom, and the yellow boxes that you see in the top panel have the exact same vertical and horizontal range. And so what this points out is that the water level decline that we saw up until the spring of 2022 was very similar to the dramatic decline we saw in the late 1990s. So the big question at that time was, will water levels continue to decline? So let's take a look at where we are and we can answer that question. So here we are in June of 2023. This is the same slide as before, where we were just a year ago. And now I'm going to add in the water level data for Superior and Michigan Huron for the past year. So with a mouse click, this yellowed area right here shows what's happened on those two lakes for the last year. So you can see Lake Superior has risen quite a bit from where it was a year ago. It's now back above its long-term average, and Michigan Huron hasn't changed very much. Now, one of the questions that's often asked that I and others that work on this project from all across federal agencies and other academic institutions is, why do water levels rise and fall? And one of the main things we look at is the combination of precipitation, evaporation, and runoff coming through the Great Lakes, a term that we often collectively refer to as net basin supply. Now, for those of you who are interested, there's a wealth of information on historical net basin supplies and other water balance features, a lot of which is maintained by the Army Corps of Engineers at this website you can see right in the middle of the page. What this image is showing that I took from that website, it's showing the net basin supply for the past 5 years on each of the major lake systems. So the top panel is Lake Superior, then Michigan Huron, Erie, and then Ontario, going back to June of 2018. Blue bars represent years that are above average, and red bars represent years that are below average, again, for what we call the net basin supply, or the net amount of water that comes from within each one of the Great Lakes basins. If we focus, for example, on just the past year, what's happened essentially since the last time we met, on Superior and Michigan Huron, you can see that Superior's water supply has essentially been above average for most of that time, including 2 years of very high above average water supplies, and that Michigan Huron has periodically been above and below that average. And this is essentially what has driven the water levels plot that I showed you earlier, causing the rise in Lake Superior's water levels and the basic maintenance of water levels on Michigan Huron relative to a year ago. This up and down of water supplies is something that we've been referring to as a tug of war on the hydrologic cycle of the Great Lakes. What we're finding in climate studies is that in general, precipitation across the Great Lakes is on average going up, but with some variability. Evaporation, the other big force on water levels, is also going up as lakes warm and we have less ice. So the way we think about that is we have two competing forces, almost like a tug of war on water levels, where precipitation wants to bring water levels up, but evaporation wants to bring water levels down. Those two forces are getting stronger, and every once in a while, there's an oscillation or a weakening in one of those forces that causes a shift in water levels. And that's a lot of what we've seen over the past year and in the previous 20 years. So let me finish up by taking a look at what we're expecting for water levels over the next several months and the next several decades. So here we are, again, showing water levels on Lake Superior and Lake Michigan Huron with the past year highlighted in yellow. With a mouse click, I'm going to add in the projected water levels for the next 6 months based on forecasts that are coordinated between United States and Canadian federal governments. So these red bars that you see here represent what we would call 95% confidence intervals for water levels over the next 6 months. And what you can see here is that on Lake Superior, water levels are expected to continue to increase. And that's based in part about the abundant net basin supply we've had over the past year, and that water levels on Lake Michigan Huron are expected to stay right about where they are. I want to take a moment to dive a little bit deeper into the origin of these forecasts, so people have an understanding of how they evolve. And one thing I want to mention as I shift slides here is that there are two very exciting projects going on right now that are being sponsored through a partnership between the Army Corps of Engineers and NOAA. One of those projects is intended to improve our ability to forecast water levels from 6 months out to a year. This is a very difficult time period to do forecasting of water levels because some of the major atmospheric phenomena that affect water levels 6 months to a year from now are very hard to predict. Things like Arctic polar vortex deformations or atmospheric blocking events we call out over the Atlantic Ocean. They're very hard to predict up to a year in the future, yet can have a profound impact on water levels. There's another exciting project through a same partnership between NOAA and the Army Corps of Engineers, improving multi-decadal forecasts. So I would be remiss if I didn't mention those existing projects. What you're seeing here is the current outlook or extended forecast that's published by the Army Corps of Engineers. The red dot represents where we are today with water levels on this plot. And if you look at the x-axis on the bottom, you can see we're spanning a period here from around July 2022, looking out about a year into the future. The two vertical axes show water level elevations in meters on the left and feet on the right. And then the lines that you see in the middle, the black line represents the actual water level for the past year. The black dots represent the long-term average water level. And then the dashed lines at the top and the bottom represent record highs and record lows. So we really are right now, right in the middle of sort of the range between record highs and lows. Now, all of these bands that you see going off to the right here represent different ways of looking at potential water levels into the future. I want to highlight two of them. One, this gray band that you see right here represents the likely range of almost all possible water levels into the future based on what we've seen in the past 50 to 80 years in terms of water supplies. The purple band, if you look at the legend down here, takes into account some of the more recent ice cover conditions we've had and matches those with water supplies in the past. And what you see is a little bit of a narrower range that if we consider what we've seen with ice covered and other conditions recently, there's a narrower range of outcomes for water levels. I encourage you to look at this website and take a little bit more at these forecasts, but this outlook right here gives, I think, a really good indication of what waters are likely to be for the next 6 months out to a year. Now, one thing we can do is we can test the integrity of this forecast framework by looking at where we were last year. So this is a slide I presented last May of 2022. This is the forecast that was issued at that time. Same general framework where the black line in the middle shows what actual water levels were right up until May of 2022. And then you have a series of these different forecasts. With a mouse click, I'll add a red dot to show where we are today. And you can see that these forecasts provided a really reasonable projection of what water levels were ultimately going to be for the following year. Looking far into the future, there's been an awful lot of work done on multi-decadal water level projections on the Great Lakes, and I'd be happy to talk about that more during the Q&A. One contribution to that is a paper that came out of our research group led by one of our students, Alex Vandeweghe, that ran hundreds, if not thousands of simulations of water level projections into the future to see whether we were likely to see water levels going down, going up, or perhaps even see a change in the extremes. This plot represents a really good representation of what we found. So what you're seeing here are a repeated simulation of 50-year periods. On the x-axis, we're showing months, so out to 600 months, but multiple 50-year simulations of potential future scenarios on Lake Michigan and Lake Huron. The gray bands that you see represent individual water level plausible scenarios going into the future. The black line represents what we saw in Lake Michigan, Lake Huron over the past 50 years as a basis for comparison. And the red line highlights just one of the thousands of gray bars that you see to give an idea of whether or not we're reproducing variability. So when we take a look at this plot, there are two important takeaways. One is that on average, we don't expect Michigan and Huron's water level on average to change much over the next 50 years compared to where it was over the past 50 years. But there is the possibility for increasing extremes, both on the high end and the low end. And you can see that in some of the gray lines there that represent these individual scenarios. Finally, I want to underscore the point that when it comes to looking at long-term water levels, we have to keep in mind that we're really asking questions about big air masses that move across North America and in fact around the world. Some of those air masses are very, very cold and dry, like the continental polar air masses. And when those come across the Great Lakes, we have a tendency for the lakes to freeze and very dry, cold air. But there are other times when warm, moist air, such as the maritime tropical air masses, can dominate and bring excessive moisture to the Great Lakes. So I think it's important to keep in mind that these are some of the key processes driving water levels. And these are the type of phenomena or things that we try to forecast, not just at seasonal scales, but at multi-decadal time scales as well. So thank you again for the opportunity to speak this morning and have a conversation. Thanks in particular to ELPC for hosting this, and also to all of our broader sponsors. And with that, Howard, I'll turn it back over to you, and I'm happy to continue the conversation and answer questions.
Thank you, Drew. That's a terrific and tight and focused presentation. I've already been getting comments back from people how interesting and important it is. I just want to pick up on a thread of something you said, which is in the past, you had talked about the trend line being modestly up in terms of water levels for Michigan and Huron. And what I hear you saying now is the trend line may not be going up, but it's the extremes that are the really important data to follow. And I always think about, I live in Chicago. Most of us don't spend a lot of time thinking about the average temperature. We think about what it's like on the really hot summer days and what's it going to be like on those really cold winter days. We don't buy clothes based on the average. We buy our down parkas based on the winter cold, and we buy our shorts and t-shirts based on the summer heat. Talk a little bit, if you would, about the extremes and how much higher and lower the water levels are, because that's what really affects the shoreline.
Absolutely, Howard. Yeah, so great question. To provide just a little bit of context, I put up on the screen here a much longer historical water leveled image. And so this is actually looking at all of the lakes going back to 1860. So if you look on the bottom axis here, you can see we start with 1860 going all the way to present. Our students just updated this plot very recently. And so while we're talking, we can take a look at the type of variability that Howard and I are referring to. A very important contextual piece for Howard, the question you just raised, and I'm sure other people have, is that if you look at Lake Michigan and Huron from about 1998 to 2013, you can see there's a very long and persistent period of below average water levels. And you might recall that there were many studies done during that time period that really flowed into this overarching narrative across the country that climate change was going to mean higher temperatures, evaporation, aridity, and drought. Now, that projection has come true for many parts of the country, but it did not come true for the Great Lakes. So just to underscore this point, there was a period where many people thought that the future of the Great Lakes meant declining water levels. And this is why we emphasize that on long-term timescales, at multi-decadal timescales, most of the studies that I and a lot of our colleagues have done have suggested that the long-term average is just not likely to change, which brings us really to the point of Howard's question, which is, well, what about extremes? And so I want to mention that there is lots of research being done right now to try to better understand whether the future is going to hold high water levels and low water levels. The general consensus so far is that the answer is yes, but it's a very tricky question to answer for two reasons. One is we're trying to run all these different future potential changes, not just in temperature, but in precipitation, cloud cover, dew point temperature, all of which affect the meteorology and the climate of the Great Lakes. The other thing that they're struggling with in terms of answering that question is we can run lots of simulations that can show a water level extreme happening, but we're not entirely sure when those extremes are going to happen. For example, we may find that over the next 50 years, water levels could set new highs 2 or 3 times, but it makes a big difference to the Great Lakes community if we know that that's going to happen 40 years from now versus 5 years right now. And we don't have a good answer to that question at this point.
You know, Drew, Tom Henry, terrific environmental reporter for the Blade
Yes.
in Toledo,
Yes.
has a question. He said Frank Quinn used to talk about the Great Lakes having roughly a 30-year, high and low water level. But what you're talking about in your graphs is a much more rapid oscillation of up and down, sort of a tug of war going between higher or lower. It's not really 30-year periods, much tighter. Talk a little bit about that, would you?
Sure. So what Tom, thanks for the question. It's great to have you joining us. What Tom is referring to, there's been a lot of very interesting research that suggests there are long-term cycles on the Great Lakes. I have not done direct research where I've done sort of calculations of cycles. But what the hypothesis of a cyclical water level cycle suggests is that the meteorological and hydrological conditions driving water levels also have a cyclical cycle. So for example, if Great Lakes water levels have a 20 to 30 year cycle, that means that precipitation and or evaporation are probably going to have a comparable cycle. Now, what we've noticed is that over the past 20 years, if that cycle did in fact exist, it has been broken. In the late 1990s, despite a profound and continued increase in precipitation, for example, the surface temperatures of the Great Lakes, I often say, went through the roof, particularly on Superior and Michigan Huron. And you can see that in this graph on the late 1990s, when water levels plummeted and then stayed very, very low on Lake Michigan Huron and then on Lake Superior as well. That below average water level period, which persisted for about 15 years, was broken with a record-setting rise in water levels. There was a combination of decreased evaporation when we had one of the first in a series of Arctic polar vortex deformations, and the lakes froze, evaporation slowed down, and water levels surged over the next several years to where we were in 2019 and 2020. And I argue that that's a very different pattern from what we've seen in the past. And I don't think it fits well into a lot of the sort of 20 to 30 year cycle paradigms that have been proposed in the past as well.
All right, Drew, now we're going to get really, water geeky, okay? Mary Ellen Miller is asking about what does IGLD mean? And I'm going to give you folks the not technical answer, but the real significance right now. That is IGLD stands for International Great Lakes Datum. And that is a careful scientific study of what is the likely highest water points, the average highest water point going up the coastal shoreline. The last datum was done for 1985. It's updated in effect every 35 years, and by 2025, there will be the new IGLD, International Great Lakes Datum, for the year 2020. That's going to be the marker every 35 years. Why this is really important is there is so much what I'll call land use and zoning and other planning decision-making built around what the IGLD is, namely, what is the area of the shoreline that's the line of demarcation between what's in public ownership, in the public trust, it's the lake and the lake bed, and what's in someone's home, private ownership, that's above the data line. Drew, do you want to talk a little bit about how that works and where you think it's going and what the impact is beyond what I've just commented?
Sure, I like the way you've summarized it. I'll show this slide again, just to add a little bit more to this idea of IGLD. The IGLD, as Howard said, is this datum reference point. It's actually the original data point is very, very close to sea level. But the reason that the Great Lakes have a separate reference datum point for all of these elevations is not only to provide good basis for decisions that have to do with water levels, but it's also because the surface elevation around the Great Lakes is actually changing quite dramatically. And many of you might have heard me talk about this before, but the short story is that 15,000 years ago, there were these heavy glaciers pressing down on the entire Great Lakes region. And as those glaciers receded, the land started to rebound. And in fact, the term that we use to describe this is called glacial isostatic adjustment or glacial isostatic rebound. And the problem or the challenge for anything dealing with elevations is that the land surface is not rebounding in a uniform way. Some parts of the Great Lakes are rising faster than others. And the water level gauging stations that go into this database right here come from stations around the perimeter of the lakes. So if you have the shoreline of a lake that is rebounding in a way like this, you have to continuously adjust the water level measurements to accommodate that isostatic or that glacial isostatic adjustment. And that's part of what Howard was referring to. So that's what I'll add there, Howard.
Yeah, and for example, there was just a case, some of you may know, the Gunderson case in Indiana, where the Indiana Supreme Court had to decide what's private property and what's beachfront that's open to people to walk on and play and picnic and use and enjoy. And the line of demarcation in Indiana is that IGLD datum point, which at present is for 1985. That will be updated for 2020. Incredibly technical scientific stuff, has enormous practical implications. Our friend Tom Henry has a lot of questions, and Tom, you get a lot of questions because of what you do. Let me see if I can move on to a couple of other people, and then we'll come back to Tom. A couple of questions of, Drew, what's the relationship between more intensive storms that are driven by climate change and water levels? I mean, is that a cause and effect, or are those storms simply, a factor point, but it doesn't make a lot of difference?
Well, so certainly there are a lot of common drivers when we think about the climate of the Great Lakes. So I wouldn't argue that water levels are somehow directly impacting the intensity of storms. Although there are interesting feedbacks between Great Lakes hydrology, ice cover, temperature, and lake events, snow events, which is sort of a sidebar. But in terms of the intensity of storms, I actually would think more about how changing in the intensity and the frequency of storm events is changing the way runoff comes into the Great Lakes. And there's actually two things that I think about as a hydrologist. One has to do with whether precipitation during the storms is falling as rain or as snow. But then if we think about precipitation that's coming in more intensely as liquid precipitation and rainfall events, it can have a tendency to wash off the land surface much more quickly, sort of to reach a soil saturation much more quickly and propagate into runoff much more quickly, which can all in all affect the hydrologic cycle and lead to a more rapid increase in water levels. The other thing I think about that isn't directly related to water levels, but I think is worth noting, is that when we have more intense precipitation events, we also scour the landscape in a different way, which changes the way pollutants come into the lakes as well. So there are sort of two important consequences on water levels and hydrology in general related to these intensifying storms.
Tom Henry's asking, about the lakes being only 10,000 years old, while Earth itself is about 5 billion years old. Just when we're dealing with those expanses of time, how much assurance do we have of stability in these sort of forecasts for the long term? The long term be not just our lives, but beyond that.
Yeah. Tom, that's a great question. I haven't done a lot of research, and I don't know others who have looked at sort of future projections going out past sort of the multi-decadal scale, right? Looking out 5,000 years, sort of relative to the past 5,000 years. There are a lot of scientists who have done paleo reconstructions on the Great Lakes, looking back 2,000, 5,000 years or so. And that's maybe a topic for another day. But a lot of folks, most of the folks I know that do water levels are primarily focused on, daily, seasonal, and then multi-decadal water level projections, probably because they do coincide mostly with the majority of decisions and budget planning decisions we're trying to make for infrastructure, human health, and protecting lives.
Speaking of the infrastructure decisions, Lucas Chamberlain and Liz LaPlante are asking about that. Yeah, how are you thinking about the difference between hard infrastructure, concrete, steel girders designed to push the water away and protect certain areas versus using softer infrastructure, wetlands restoration and other things that are designed to more, buffer the shoreline, but not just move water around? Talk a little bit about that, would you, Drew?
Yeah, sure. So much of what I'm about to articulate comes primarily from my personal views that I've developed over the years, looking at this question and looking at different property ownership propositions. In general, I would argue that in highly urbanized environments where there's already a lot of infrastructure, continuing to, the term is hardening the shoreline, but continuing to build up robust infrastructure in cities like Chicago, Cleveland, Toronto, it makes a lot of sense. And that the infrastructure planning needs to account for future high water levels and future low water levels. But I also believe there are other areas of the shoreline, particularly look at highly erodible shoreline along Lake Michigan, where I think managed retreat is a very important option to consider. So much of the Lake Michigan shoreline is privately owned, and that leads to a conflict, I think, between access to that shoreline and appropriate management of housing and commercial infrastructure that is really susceptible to a lot of damage when we think about how erodible those shorelines are and how fluctuating, how variable water levels have been and can continue to be. I think there needs to be a serious conversation about more communal ownership of some of that land and retreating a lot of the infrastructure from these highly erodible shorelines.
Drew, I've come to appreciate the interactions between not just water levels, but winds. And as you're talking about the Western Michigan shoreline, keep in mind the winds are blowing principally from the west to the east. So when we have from climate change, more intensive storms, higher wind speeds, bigger waves, to some degree, that's less of a problem on the, Wisconsin Lake Michigan shoreline. It's much more of a Western Michigan issue in terms of the eastern part of Lake Michigan, where the water levels are higher, and then the winds and waves are really battering the shoreline. Is there a lot of research that's sort of looking at the combination of meteorological patterns in terms of winds, waves, more intense storms, and water levels? Is that something that you and your group are doing, or are there others who are working on that as well?
Great question. So I would say that the group, the team, or the aggregation of scientists that are addressing this question involves a huge array of content expertise. There are some folks who look at long-term average water levels, and that's one thing that our group does a lot of with folks from the Army Corps and NOAA. But there are also folks who look at short-term water level variability from storm events. Compounded on top of that, there are folks who look at the erodibility and the soil structure of different shorelines. And then on top of that, there are people who look at changes in ice cover. So you can imagine that there are time periods where we have severe storms that during some years are buffered by shoreline ice. As we see coastal ice cover becoming more variable and on average decreasing, there is a tendency for these storms, particularly those in the winter, to have an exacerbated effect on the erosion of the shoreline. So yes, our group does do a lot of this work, but we do it in concert or in combination with other experts in that full array of content that I mentioned. One other thing that I want to mention on this is that the more we do research on the erodibility of shorelines, particularly on the western shoreline of the state of Michigan, one of the important things to note is Howard, you know this, and a lot of other listeners might know this, but some don't, which is that erosion is a natural process, that shoreline is eroding at a relatively high rate from a geological timescale without us doing anything, or without there being impacts of climate change or less ice. Some of the things that I mentioned and that you are asking about, higher winds, more intense storms, less ice, are exacerbating what is already a natural rate of erosion along those shorelines. And I think that's such an important point when people think about how they're going to be interacting with building homes or commercial establishments along that shoreline.
Drew, as you're saying that, I'm looking at the photo that's a backdrop, of your screen behind you, which is exactly that sort of case. And the analogy that I use, it's not perfect, is that, in a place like Chicago, the roads, the highways get eroded very fast because of the heat and cold, the freeze and thaw cycle, where little cracks develop in the road and it gets water and ice expands it. That becomes a big hole and a big pothole, and then they have to fill it, and the heat sort of creates pressure as well. That's the effect of the ice conditions you're talking about on the shoreline. It's just exacerbating what is otherwise natural erosion. And Newt Nadelhofer, your colleague and mine, has a question for you about the increasing frequency of rain or snow events. The published research indicating that's sort of a double whammy, that winter rains melt snow, increase pollutant exports from the landscape to the lake during the winter when the plant roots uptake nutrients, especially nutrients, nitrogen and phosphorus. Do you want to talk about that a little bit, of the rain snow effects on the lake and what gets into the lakes?
Well, sure. It'll be hard for me to talk a little bit about it because it is such a complex problem, as Newt was alluding to. Before we deal with pollutants, one of the challenges we face in hydrological modeling at seasonal scales is trying to understand whether or not the change in the timing of the accumulation of snow and the melting of snow, even if we have the same total amount of precipitation over a given year, actually leads to a change in the water balance. For example, let me put it a different way. If we have a typical or historical year where snow accumulates into March and April and then suddenly melts and leads to a big spring runoff, is that going to lead to a different long-term water level regime than a climate in which some snow falls in December and January, but then melts or is washed off into the lake as runoff? Some of the simulations we've done suggest that how and when snow accumulates and how and when it melts, even with the same total amount of precipitation, can actually lead to a long-term and permanent shift in water levels, just due to the change of timing of snow melt snow accumulation and snow melt. So I think that was part of what Newt was asking. And that's about as short an answer as I can give. Certainly, as Newt alluded to, there are also severe implications, not just for pollutants, but other things like spawning habitat and when ecosystems expect water to be coming in and the temperature at which they expect water to be coming in from rivers and streams into the lakes. These are all impacts that are directly related to the changes in the magnitude and the timing of snow as it falls, as it accumulates, and as it melts.
Why I love working with the University of Michigan scientists. Go blue. Question being asked about Lake Superior. And the way the question is framed is, I think, right on target by Mary Kay Baker, which is, how much truth is there to the, well, they opened the spigot from Lake Superior to Lake Michigan and Lake Huron to try to alleviate pressure on the shoreline on Lake Superior on high water years. And what that then does is lead to worse problems in Lake Michigan and Lake Huron. Do you want to talk about that a little bit?
Sure, it's a really good question. And to answer it, I'll pull up again here a slide that I've shown in the past that shows the long-term historical water levels. One point that I didn't make, but I'll take this opportunity to make, is that when we look at this long-term water level plot, it's important to note that Lake Superior and Lake Ontario are regulated. In other words, the outflow has a moderate amount of control. That control on Lake Superior was put in place in the 1920s or so. So I don't know if you can see my hand floating on the screen, but in the top panel there, right around here, is when at Sault Ste. Marie, control measures and structures were put in place to help regulate the outflow of Lake Superior. And then similarly, if you look all the way at the bottom down here in the 1960s, the Moses Saunders Dam and some other infrastructure was put in place to regulate the outflow of Lake Ontario. Now, I want to answer this question by saying, first and foremost, the impact of outflows was much more significant on Lake Ontario. And you can see that here, where you see the dampening and a change in the range of extremes on Lake Ontario following the 1960s. On Lake Superior, the impact is much more minimal. And if you're looking for sort of a quantification of that, I would steer you towards great research that's been done by the International Joint Commission, or the IJC. They've been looking a lot at sort of the ability of Lake Superior regulation to impact long-term water levels. And the short answer is that while there may be very, very short-term ways to hold up or the amount of flow coming out of Lake Superior or let a little bit more out, the short answer is there's really not much you can do with Lake Superior control to impact water levels on Lake Michigan and Lake Huron and further downstream.
Drew, talk a little bit, if you would, about how water flows through the system of the Great Lakes. If you grew up in the Midwest, all of us remember Holmes, Huron, Ontario, Michigan, Erie, and Superior. Has the pathway by which water flows through from Superior to Michigan, Huron, to Erie, to Ontario, is that speeding up? Is the turnover of water accelerating, or has that stayed relatively stable?
Great question. So to answer that question, I'll show this plot just for visual reference here for people. On the left-hand side, we have a map of the Great Lakes showing those net basin supply numbers I showed. But to answer Howard's question, on the right-hand side, we're looking at the rate of water flowing out of each of the Great Lakes into the next downstream lake. So for example, over here, flowing out of Lake Superior into Lake Michigan, Lake Huron is the St. Mary's River. These numbers indicate thousands of cubic meters per second. So about 2,200 cubic meters per second of water flowing from Lake Superior into Michigan, Huron. Water, as Howard alluded to, continues to flow down through Lake Erie, down over Niagara River at a rate of 6,300 cubic meters per second, and then out of the St. Lawrence River. So from long-term timescales, these represent long-term averages. And I would say that they have these long-term averages haven't changed much. Certainly over short time periods, over a year or two, when there's abundant water in the Great Lakes, these numbers can go up quite dramatically. In fact, when there was extreme flooding on Lake Ontario in 2017 and 2019, the outflow from the St. Lawrence River reached 10,000 cubic meters per second. That's an extraordinarily high flow. But on average, I would say that these numbers tend to be pretty close to what the averages are that we experience over the past several years and going into the future.
Thank you, Drew. We're about out of time right now, and I just want to thank all of you for joining us today, and Professor Drew Gronewold, not just for joining us, but for the work you're doing. It's really important. It's absolutely vital. This is a priority for the Environmental Law and Policy Center. We've had the pleasure of working with Professor Drew Gronewold for about half a dozen years now. The Great Lakes is where we live, work, and play. It's absolutely vital to our region. It's a global gem. It's an impact in terms of the economy, our ecology, and what the water levels are and how much they oscillate up and down makes an enormous impact upon, the built infrastructure along shorelines and the policies we use in order to protect our environment and protect our communities. So thank you, Drew Gronewold. This is posted up on Facebook, so you're going to be able to send it along to your friends. Take another look at it if you want. Thank you for joining us for this ELPC Thinks webinar. There'll be more to follow, and you'll be getting a follow-up email this afternoon from our terrific communication staff and Mary McClellan and Libby Prakel. Thank you all for joining us. Take care.